we have learned how a moving magnet towards a coil brings current in the coil circuit as it indicates deflection in the galvanometer needle. Now we will learn another activity in which the moving magnet is replaced by a current carrying coil and the current in the coil can be varied. So let us see how it is. Here we will take two coils. Previously, we have taken one coil and other was bar magnet. So here in place of bar magnet, we will take another coil. So we have two coils. That is why it is named as coil 1 and coil 2. So we have to take two different coils of copper wire which have large number of turns. It can be 50 and 100 respectively. For one coil we can take 50 and for the other we can take 100 turns. Now we have to insert them over a non-conducting cylindrical roll. So as you can see in the figure, there is a big cylindrical roll. You can take a thick paper roll for this. Over this cylindrical roll, we have to insert these two coils. Now with coil 1, we have to connect a battery and a plug key in series. Now students, here we need to keep in mind coil 1 will be large number of turns. As I have mentioned that you can take one of 50 and another of 100 turns. So which is of more turns, with that we will connect a battery and a plug key. And with the second coil we have to connect a galvanometer. This all are shown in the figure. Plug in the key and then we have to observe the galvanometer. Will you see any deflection in the needle of a galvanometer? You will observe that the needle of the galvanometer instantly jumps to one side and just as quickly returns to zero. Please be careful for learning this. As you plug the key, the needle of the galvanometer quickly moves towards any side and quickly it returns back to zero, indicating a momentary current in coil 2. Now, if you observe properly, the galvanometer is attached with coil 2, right? Which means the galvanometer will detect the presence of electric current in coil 2 only, right? Because it is attached with coil 2, right? And as I said, the observation will be quickly on one side and then quickly it comes back to zero, which means there is a momentary deflection. For a moment there is a deflection in coil number 2. Now if you disconnect coil 1 from the battery, you remove coil 1, what will happen? You will observe that the needle momentarily moves but to the opposite side, which means when we remove the battery from coil 1, then also coil 2 will have electric current, induced electric current, and that is why there will be a momentary deflection of the needle but to the opposite side than the previous one. What does it say? It says that now the current is flowing in the opposite side, opposite direction than before. It will be in which coil? Coil number 2, because the galvanometer is attached with coil 2. In this activity, we observe that as soon as the current in coil 1 reaches either a steady value or 0, the galvanometer in coil 2 shows no deflection. Okay, in coil 1 we have attached a battery and a plug key, so obviously electric current will move, and as there is electric current in coil 1, it shows the electric current's presence in coil 2 also. What do we conclude from this? We conclude that a potential difference is induced in the coil 2 whenever the electric current through the coil 1 is changing. Now, if the electric current in the coil 1, if it is reaching towards a steady value or towards the 0, by that time in coil 2 it will show 0 deflection. Are you getting what I'm saying? In coil 1, that at the time by which it is getting steady current, constant, or else 0 value, and at that time the galvanometer in the coil 2 will show no deflection, right? So we conclude that a potential difference is induced in the coil 2 whenever the electric current through the coil 1 is changing. If there is a change in the electric current in coil 1, that time only coil 2 will have deflection in the galvanometer. Okay, and when can the electric current changes in coil 1? In the starting or at the time of stopping. Okay, so coil 1 is known as primary coil and coil 2 is known as secondary coil. Why coil 1 is called primary coil? Because the current is passed in the coil 1. That is why it is primary. And deflection is observed in the coil 2. That is why it is the secondary coil. Now, one thing you need to keep in mind, whenever there is a change in electric current in coil 1, that time there will be deflection in the galvanometer for coil 2. So, as the current in the first coil changes, the magnetic field associated with it also changes. Why magnetic field is here? Because we have taken a coil of large number of turns and we have learned before in this chapter that it produces magnetic field. That is why this is happening, that in coil 1 we are producing current and in coil 2 it shows deflection. So the answer is, as the current in the first coil changes, the magnetic field which is related to it, that will also change, right? And that is why magnetic field lines that are also changes. And as coil 1 and coil 2 are attached together on a cylindrical roll, the magnetic field lines of coil 1, that is closest to magnetic field lines of coil 2 also, right? So because of change in magnetic field and field lines related to primary coil, the secondary coil is also produces electric current in it. And this process by which a changing magnetic field in the conductor induces a current in another conductor is called electromagnetic induction. Now this is the proper definition which you all need to remember well. What it is? It is the process by which a changing magnetic field in a conductor induces a current in another conductor. That is called electromagnetic induction. Now conductor, here we have taken coils, coil 1 and coil 2. So there is a change in magnetic field for coil 1, and that is why it makes this coil 2 to induce electric current, to produce electric current because of changing magnetic field. So this is the process which is known as electromagnetic induction. And by this picture you can clearly see it. In the first coil, we have a battery and a key attached to it, and you can observe the magnetic field lines around it. Now you see coil 1 and coil 2, the magnetic field lines are attached together. That is why the change in magnetic field in coil 1 will produce electric current in coil 2 also. I am sure that by this figure you can understand it easily. Now, the induced current, the current which is produced, is found to be the highest when the direction of motion of the coil is at right angles to the magnetic field. This is very important to remember. What it is, it can be asked to you when the induced current is highest, maximum, when it can be. So answer is the induced current is highest, maximum, when the direction of motion of the coil is at right angles to the magnetic field. And we can use a simple rule to know the direction of the current. So let us learn the rule to know the direction of the induced current. For this, we have to stretch the thumb, forefinger, and middle finger of right hand so that they are perpendicular to each other as shown in the figure. So here we are learning Fleming's right hand rule. Do not mix all the rules together. This is Fleming's right hand rule. For what it is used? It is used to find the direction of induced current. Okay, for this what do we need? Right hand's thumb, forefinger and the middle finger. If the forefinger indicates the direction of magnetic field, look at the figure. Thumb shows the direction of the motion of the conductor, and the middle finger will show the direction of induced current. So students, for remembering this, you need to remember that these three fingers should be perpendicular to each other. Okay, you have to stretch the fingers in such a way that these three fingers are perpendicular to each other. Then only you can get the direction of induced current. And what do you have to think? That the forefinger is the direction of the magnetic field and the thumb is the direction of motion of the conductor. And then if you keep it in such a way, then the middle finger will show the direction of induced current. And this is Fleming's right hand rule. Now, let us again remember that the induced current is found to be the highest when the direction of motion of the coil is at right angle to the magnetic field, when it is perpendicular. Right angle means when it is perpendicular. Now, let us once again recall Fleming's right hand rule. What do we have to do? We have to stretch three fingers of right hand in such a way that they are perpendicular to each other. And if we stretch them in such a way, then the forefinger, first finger indicates direction of magnetic field, and the thumb shows the direction of motion of the conductor. And that is why the middle finger will show the direction of induced current. And this rule is known as Fleming's right hand rule. For what this rule is used? To find the direction of induced current.